So maybe we can slowly start. So let me welcome you all to this second session of the Brazilian Probability Seminar. So I just remind you that if you have any question, you can just write it on the chat, and I will then stop Franco and ask the question. So, yeah, well, it's a great pleasure. We had the first session, Antonio Galvez, which probably is the most experienced Brazilian researcher in probability. Now, I think we have the youngest one, Franco Severo, who just defended his PhD thesis a month ago in Paris and University of Geneva. And so, well, it's a great pleasure to have Franco with us today. And he will speak, well, his title, it's on the screen, so I won't repeat it. So thank you very much, Franco, for accepting this invitation. It's a pleasure to have you.
Thank you, Claudio, for the introduction and the invitation. It's a pleasure to talk to my fellow Brazilians. This is first of all a joint work based on a joint work with Hugo Dominic Copin, Shubhajit Goswami, and Pierre-François Rodriguez. I will just make a disclaimer first of all, because this is a little bit a different style of talk. I will not focus so much on the result itself. I will focus more on the technique. So for a large part of the talk, or almost all of it, it's going to be a little bit vague. I will try to describe the general idea in a very large context, and then I will explain, just give a little touch on how we implemented it, like in a specific case. So I hope it's not going to be too vague. I hope I pass some message. So first of all, I would like to talk about sharpness in percolation theory, which is the main phenomenon we want to study. And I will give a very quick introduction on that. And then I will describe this technique called interpolation that we have used to prove sharpness for some specific kind of percolation model. So, okay, so let me get started. So here's the, what you probably already know is the classical percolation model, which is the Bernoulli percolation. It goes as follows. We start with the hypercubic lattice, ZD, for dimension larger than 2, because dimension 1 is not interesting for this model. We fix a parameter P between 0 and 1, and then we keep each edge with probability P, and we remove it with probability 1 minus P independently for each edge. So it's an independent percolation model in the sense that every edge has an independent state. And like that, we have a random subgraph of ZD, okay, that depends on the parameter P, which is the density of this subgraph. Then we want to study the connectivity properties of this random subgraph. Okay, so let me just introduce some nomenclature. I will often call edges that are kept, I will call them open, and edges that are closed, I will call them, edges that are removed, I will call them closed. And connected components, I will call them clusters, okay? So that there is no misunderstanding when I use these expressions later. So we want to study essentially the clusters of this random subgraph, okay? And here is some simulations for different values of P in 2 dimensions. In black, you see the edges that are kept. So you're seeing it from far away. It's a very large box. You can see there are some clusters, some connected components. And in red is the largest connected component inside of this box. Okay. So for P equal 0.3 and 0.4, you see the largest connected component is quite small, actually. And for 0.6 and 0.7, you see that it's suddenly a huge, actually, connected component. The largest connected component is kind of everywhere. And the other components, they exist, they are in black, but you see they are small, they're quite tiny. So this is what you see from the simulations, and this motivates the introduction of the following quantity, which is a central importance in percolation, which is the critical point, PC, that depends on the graph. So in this case, it depends on ZD, which is the supremum of values of P, such that there is no infinite connected component, almost surely. Okay, so one can prove that this is indeed a meaningful definition. So it's a value between 0 and 1 strictly, and therefore below this critical point, we have what is called the subcritical phase, on which we have only finite clusters, so all the clusters are finite. And above this critical point, we have the so-called supercritical phase, on which there exists at least one infinite cluster, okay, by the definition. Okay, but if you look at the simulations, actually you see something a little bit stronger than that, right? If you look at the first two pictures, you see it's not only true that every cluster is finite. Every cluster looks very small, like they are tiny in some sense. There is no cluster that is kind of occupying everything, even being finite. And in the supercritical phase, you see that there is essentially only one infinite cluster, and it's occupying everything. And the finite clusters, they are tiny. Okay. So this suggests a stronger notion of subcritical and supercritical phase. So it seems that subcritical phase is actually strongly subcritical in the sense that the clusters are tiny in some sense, and the supercritical phase is strongly supercritical in the sense that there is only one infinite cluster, and the finite clusters that live outside of it are tiny. Okay, so this is the intuition, and this is what's called a sharp phase transition, when the subcritical phase is strongly subcritical and the supercritical phase is strongly supercritical. And this, for this specific model, the Bernoulli percolation has been formally proved. So for the subcritical phase, this goes back to the 80s. Menshikov and Aizenman and Barsky proved that indeed for every P smaller than PC, the radius of a cluster decays exponentially in probability. So the probability that, say, the origin, but you could fix any vertex here because it's a translation variant. The probability that the origin is connected to distance n, so this is just the boundary of the box of radius n. So the probability that the origin is connected to distance n decays exponentially in n. So you see in a large box, typically the largest cluster you're going to see it will have logarithmic diameter. So this formalizes the notion of tiny clusters in the subcritical phase. Okay. And for the supercritical phase, a result by Grimmett and Marstrand guarantees that indeed locally, when you look at the box, one has a unique macroscopic cluster, and this happens with extremely high probability. So I will not come to the details of what local uniqueness here means, but you just think that in a box of size n, there is only one cluster that is macroscopic and all the other clusters are small. Okay. So and you can even prove that more specifically that the finite clusters are tiny in the sense that if the origin is connected to distance n and it's not in the infinite cluster, so it's not connected to infinity, then this probability also decays exponentially in n. So this also tells you that you have this uniqueness of infinite cluster. So the uniqueness of infinite cluster, I should say, this was proved before Grimmett and Marstrand, but the most interesting thing is that this is strong uniqueness which is the fact that the finite clusters are tiny. This was really proved by Grimmett and Marstrand, and this is what I mean by that. So that being in a finite cluster, in a large finite cluster, is extremely unlikely. Okay, so again, typically finite clusters will have logarithmic size in a box. Okay, so this is what's called sharp phase transition. Are there any questions about what it means to have a sharp phase transition? Or
statement? For the moment, Franco. I think it's very clear.
Okay, great. So this is the main phenomenon I want to study. Here it is. So okay, so it's a theorem for Bernoulli percolation, but there are other percolation models, many other percolation models, for which we have some dependencies in play. So here we have each edge is independent of each other. Things are a little bit simpler, but when you start studying percolation models with dependency, then this starts to be more and more complicated as you advance. So let me mention some other percolation models. So I will just mention, so there are really many percolation models in the literature. I would not be able to talk about all of them. So I will just mention a few like more classical ones. So first, the FK percolation or random cluster model. It has two parameters, Q larger than 0 and P between 0 and 1. So you should think of Q fixed, okay? And P you vary between 0 and 1, and we'll have some PC as before, and you can ask the same questions. And the model is defined as follows. So it's again a probability measure on subgraphs, which we call omega, okay? And the probability is distributed as proportionally to P to the number of open edges, 1 minus P number of closed edges. So up to now, it looks like Bernoulli percolation. Every edge is independent of each other, it looks. But then there is this term Q to the number of clusters that introduces some dependency in the model. So if Q is equal to 1, then this is just Bernoulli percolation. But if Q is different from 1, this term introduces some dependency, and this is a correlated model that where correlations can go even to infinite distance, potentially. Okay, so this is a classical model. It's very important in statistical physics because it's related to the Potts model. For those who know, so it's a classical and very important percolation model. Another classical percolation model is Voronoi percolation. So there it's in the continuum, but it's not hard to understand why it's called the percolation model. So it goes as follows: you have a process eta, which is a point process of intensity 1 in RD. Then you can construct the Voronoi cells associated to this point process. So the Voronoi cells, for those who don't know, is just the set of closer to this to a given point of your Poisson point process. Okay, so this decomposes the space into cells centered at those points. And then for a parameter P between 0 and 1, we consider each cell open or closed independently with probability P and 1 minus P. So like before. So it's like a Bernoulli percolation, but just in a random environment, in a random graph, if you want, or something like that. There's also the Boolean percolation, which is also in the continuum. So we fix first a probability measure on the radius of which will be a radius of balls in 1 minute. Then for lambda larger than 0, which will be our parameter instead of P, we consider a Poisson point process lambda on RD, and then we put balls of radius distributed as mu independently, centered at each point of the Poisson point process. Okay, so you essentially just sampling in a reasonable uniform way balls in your space, and you're covering parts of the space with these balls in a random way. And then you can look at this occupied set, this set occupied by boxes. And this, as lambda increases, you see that this occupies more and more space. So you expect that there is some phase transition there. And you can also look at the vacant sets instead. So the complement of the occupied set. So both are reasonable percolation models. And in all cases, you just want to study properties of connective properties of the open set or occupied set or vacant set for whatever model you pick. Okay, and there are many other examples that you might have heard about. So random placements, Gaussian free field level set. I will come back to that because that's the model we have studied specifically. Loop, soup, Volta percolation, level sets of smooth Gaussian fields. There are really many percolation models around. So okay, so you don't really need to remember the definition of these things. Okay, I will not really talk about them. I just want you to see some definitions of other notions of percolation. Okay, and for you to know that you can play around with these things, and there are other models that are interesting in their own, but for which you have dependencies. Okay, so in each of these models, you have some notion of dependence that's not present in Bernoulli percolation, and therefore they are harder to analyze. Okay, so let me mention some known results concerning sharpness of phase transition for these classical models. So as I mentioned, for the subcritical sharpness, oh, by the way, I didn't say that explicitly, but when I talked about sharpness, so let me come back. Sharpness here I call both results. Okay, the subcritical sharpness. So for whatever model you're talking about, the analog of this. Okay, and this. Okay, so both results I call sharpness, but I call the first one subcritical sharpness and the second one supercritical sharpness. Okay, just because one is the subcritical and the other is supercritical. Just want to make that clear because in the literature sometimes people call sharpness just the first result. So I want just to make it very clear that here, when I say sharpness, I mean both, and I will specify which when necessary. Okay, so let me come back to known results. So for the subcritical part, so for the fast decay of cluster size in subcritical phase, there are many results available for all those models. So as I mentioned, for Bernoulli percolation, it was proved by Menshikov and Aizenman and Barsky, and actually for dimension 2, it had been already obtained by Kasten. For FK easing, so the FK model with Q equal 2, which is called FK easing because it's related to the easing model. This was proved by Aizenman, Barsky, and Fernandez. For Voronoi percolation, FK, and Boolean, you see here results in dimension 2 coming first, okay, by these people. And then finally, a result for the 3 models in all dimensions recently by Dominique Copin, Raoul Fientation. So you can see that usually dimension 2 comes first, and then someone comes and proves it in higher dimensions. So dimension 2 has something special, which is called duality. For those who don't know, I won't have time to get into that, but it's a special property that allows you to relate a model with a dual one living on the same space, and these two guys are related to each other, and you can essentially reduce the whole study of the model to crossings of certain boxes, and this simplifies the study. Okay, so you see dimension 2 is usually proved first, and then comes higher dimensions. And this last result, I would like to emphasize that it was really a breakthrough. It was a new technique to prove sharpness of phase transition, which essentially proves it for any model previously known and many others. It has some limitations, but it really improves by a lot the techniques developed before in terms of robustness. Okay, so these are, I think, the main results concerning subcritical sharpness. For supercritical sharpness, the thing is a little bit less developed. So first of all, in dimension 2, again, there is this notion of duality that allows us to relate subcritical phase with supercritical phase. So in those 2D models, usually proving subcritical sharpness kind of implies supercritical sharpness. This for the dual model. So it's more interesting for supercritical sharpness. It's more interesting in higher dimensions. And for Bernoulli percolation, as I already mentioned, this was proved by Grimmett and Marstrand in 90. And the only other model for which I know, maybe I'm wrong, maybe there are others, but the only model I'm aware of this has been obtained is the FK model, but for Q equal 2 only, so the one related to Ising model. So this is due to very special properties of the Ising model that allows for better understanding of the model. So okay, so you can see that the supercritical sharpness is a little bit less developed, the study of it. Okay. So this is just a quick overview of sharpness for correlated models. And what is this talk about? So this talk is about, sorry, just a second. This talk is about a new technique for proving sharpness of phase transition for correlated models. Okay, so think any of this or even your favorite correlated percolation model, and imagine you want to prove sharpness for it. Okay, so an approach that we're going to follow is to truncate the model. Okay, so to first study a finite range model, so a model with correlations that go up to a finite, like bounded distance. Okay, and then by approximating any model by finite range, import the sharpness from finite range to the original one. So I will make that a little bit more precise, but not too much in the following slides. So first of all, let me talk about finite range models. Okay, so now it becomes a little bit more abstract. We consider mu any percolation model. So here I mean just a family, a parameterized family of percolation measures. Okay, for now it's that level of abstract.
Well, let me interrupt you. I have a question from Anna Paula. She's asking, in Boolean percolation, does probability of the one-arm event decay exponentially?
For Boolean percolation, that depends on the, that's a good question, thank you. That depends on the distribution of the radius. So it decays as fast as the distribution of the radius. So that's because of course, if you can always just put one ball, and this will allow you to go to distance, whatever radius of that ball is. So you can only expect decays to be at most the decay of the radius distribution, so the mu here. And this is true, okay, with some assumptions. With some assumptions on mu, you can prove that this is indeed true. So it's exponential if, for example, mu has exponential decay, but it's not if mu doesn't. I hope it's.
Oh, thanks.
Okay. So let's come back to finite range model. So consider mu just an abstract percolation model, so a family of percolation probabilities. So just probabilities on subgraphs. Okay. And we're going to consider some properties. So first, some standard assumptions on percolation theory. We assume the model to have some lattice symmetry, so invariant with respect to reflections, translations, this kind of things. Positive association, which is a very helpful property in percolation theory, so we're going to assume that. And finite energy, which is just tells you that you can do local modifications on the model with positive probability. I won't define this in details because I don't want to put emphasis on that. So just imagine there are some classical, like standard assumptions on percolation theory. Okay, and now comes the most interesting assumption. We're going to assume that it has a bounded range IID encoding. So we're going to assume that this measure mu can be obtained by just applying a bounded range function on an IID bit, okay, on IID random variables. So you think that you have IID random variables on each edge, and you have some function that goes from the percolation configurations. So here you can think 0 as a closed edge and 1 as an open edge on itself, and assume that it's bounded range, so that the state of an edge depends only on the edges at distance, say r from it, for r some universal constant. Okay, so in particular, mu p itself is finite range. It has finite range correlations. So if you take edges which are at mutual distance larger than r, then the state of those edges are independent. If you go to distance closer than r, then they may not be independent. But if you have distant edges, then they're independent. Okay, so I hope this is clear. Is there any question about that?
No, I think it's clear. Milton has a question. Can you comment on the suitability of the positive association assumption in correlated percolation?
Yeah, this is a limitation of our techniques at the moment. I mean, when I say our, I mean almost the whole community, with a few exceptions. So it should not be morally. It should not be an important assumption. So that's the answer. So it should not be such an essential property to derive many results, but we get quickly stuck without it. Again, with very few exceptions in the literature. So it's yeah, we lack development in this. There have been, so let me just mention, there have been some progress by Befarra, Gaillet, Muirhead, Vannevi, and Rivera. But yeah, so rather limited for now. In any case, for this talk, maybe don't pay too much attention on the assumptions and and just maybe just get a big picture. That's more like what my goal here is just to give a kind of a big picture. Okay. Okay. Thank you for the question. Okay, so this is the most important assumption I would like you to pay attention to, is the bounded range IID. And actually, I would not even ask you to pay attention to this too much, just to remember this implies that the model is finite range. That if you take edges at mutual distance larger than r, then they are completely independent of each other. So that's the key property I want you to remember. All the others you can kind of forget. Okay. And the third assumption is a sprinkling property. So this is just essentially just for the model to make sense, because of course you can always define this family to be a constant in P. Then of course you don't have any phase transition. So this is essentially just saying that the dependency in P makes sense. So when you increase P, you increase the model in some sense. Okay. So we formalize this by the following statement. If you take P smaller than P prime, then there exists some absence such that the model at parameter p prime stochastically dominates the superposition of a model at parameter p and a Bernoulli percolation of parameter epsilon. Okay, so this is just one way of expressing the strict monotonicity in p in some sense. Okay, so if you assume all these properties, then sharpness, then one has sharpness of phase transition for this model. Okay, and this is not, I mean, I stated this is a theorem, but it's not a big theorem by us. It's all the job has been done by these smart guys here. So we just do almost a standard adaptation of results of the proof of Grimmett and Marstrand for Bernoulli percolation, and for the subcritical phase we adapt the recent breakthrough by Dominique-Copin, Raouf, and Tassion. So these guys made all the hard work. We just adapt the techniques in a standard way. We managed to prove that essentially, roughly speaking, any finite range model has sharpness. Okay, so this is how I want you to remember this. So again, there are assumptions. There are many assumptions here that are, some of them are unpleasant, like positive association, as Milton pointed out. But for this talk, just roughly speaking, just keep in mind that finite range implies sharpness in some sense. Okay. So this is of course not the main result I want to talk about. It's kind of a not so difficult consequence of previous works. But now the interesting thing about this is that we can ask ourselves, how do we prove sharpness for models with long range correlations? And then if you have this result in mind, then there is a very naive strategy, which is exactly the strategy we're going to follow, which is a very naive strategy, which is just, okay, we have it for all finite range models. Given a long range model, can't you just truncate it and import the result from finite range to infinite range? Okay, so that's going to be our goal. So this is going to be our interpolation idea. So okay, so from now on, let mu be a percolation model possibly with long range correlations, and think of one with long range correlations. And we want to prove that it undergoes a sharp phase transition by comparing it with a finite range model. Okay, and we are going to do that as follows. So first, we're going to consider an interpolation. So let me just introduce what I mean by interpolation. Interpolation is just a family of models indexed by t that goes from 0 to infinity, included, such that first, the last model, phi infinity, is just mu infinity is just the original model mu that you want to study, and each mu t is a finite range model. Okay, so it's so maybe think in your mind that mu t has range t, for example. Okay, so you should think mu t is a model for which we know how to prove sharpness. Okay. And then our strategy will be the following. We construct first a good interpolation in some sense, so that the mu t's are really like good approximations of mu. And then for connection events A, so percolation events like zero connected to distance and this kind of things, we prove a differential inequality for the function that to which P and T associates the probability of A. Okay, and if we prove a good enough differential inequality for this function, then we will be able in the end to compare the original model with a truncated one, maybe changing slightly the parameter P. Okay, and if we do so, then we can use this comparison to import sharpness from ut to mu. Okay, so this is, generally speaking, the strategy. So let me be a little bit more precise about this differential inequality we're going to derive. So again, for connection events A, we're going to be interested in the following differential inequality. We're going to upper bound the derivative in t by something, some constant depending on t, times the derivative in p. Okay. So you should think here that the derivative in p is positive because there is some monotonicity in p, and the derivative in t is not necessarily positive because it's just changing the model, so it could increase or decrease the probability, whatever. So then that's why there is an absolute value, and we want to do that for a function f that's integrable. Okay. Okay, why do we want that? Well, it's very simple, because if we have that, then we can integrate this differential inequality from t to infinity, and change p by just a little bit, which is just the integral of f, and we have some kind of monotonicity for this function. Okay, as a direct consequence of this differential inequality. So just integrating it, you get this comparison between the original model and the truncated model at slightly perturbed parameters p and p plus epsilon, where epsilon goes to 0 as t goes to infinity, because it's just the integral of f. Okay. So if we prove this differential inequality, we get this comparison. And if we get this comparison, then I let you think about it, but it's not so hard to derive sharpness for mu from the fact that each mu t for fixed t are have sharpness. Okay, so that's essentially the strategy, and everything reduces to this differential inequality. Okay. So are there any questions about the general strategy and the differential inequality?
Well, no questions for the moment.
Okay, good. So now our goal is proving this differential inequality, right? Okay, so how are we going to do that? Well, the nice thing about this is that usually, so I didn't explicitly define an interpolation. Everything here is very abstract, but in practical circumstances, like in real life, you're usually gonna have a kind of natural family interpolation mu t, and the derivatives in t and p will not be so complicated to analyze, okay, or maybe to express in terms of probability of something. So usually you will have something like a Russo's formula. For those who are used to Russo's formula in Bernoulli percolation, it's something very similar. One expects that for any reasonable interpolation, that will be something like that. Okay, so roughly speaking, one will often be able to write something like this, that the derivative in p is just the sum over x, and then the probability that x is p pivotal for a, whatever p pivotal means for now, and the derivative in t is the same thing, but for being t pivotal. And what do I mean by pivotality here? So again, since this is a very abstract context, there is no notion of no precise definition, but roughly speaking, this will be something like the following. It will be something saying that a slight change in p, for p pivotality, a slight change in p around the point x changes or affects the occurrence of the event A. And for t pivotality, the same thing, but for a slight change in t. Okay, so it's natural if you think of it like expression of derivative. You take it at p here, and then in p plus epsilon, then it's divided by epsilon. You know, you're gonna see something like, okay, around some point, changing P slightly modifies the event. So you get some expression of this form. Of course, the notion of P pivotality and T pivotality will depend on the model. It will be more and less complicated to analyze, but roughly speaking, it will mean always kind of the same thing, which is what is written here. The slight change in that parameter changes the occurrence of the event. But the advantage now is that it is something centered at some vertex x. So it's a notion that depends on the vertex, and it's kind of localized. It's something that depends on the whole space, but the interesting things are happening at the point in some sense. Okay, so it's at the point x that something is happening, that changing P or T respectively will kind of change the occurrence of the event. Okay, I'm sorry for being very vague here, but there is no way of not being vague with this level of generality, and I would like to give an idea of the strategy in a large context, not just in one specific model. Okay, so then you have this formula for derivatives, and then the differential inequality we want to prove could be reduced just to this comparison between T pivotality and P pivotality. So for every x, you can prove that T pivotality is smaller than this function T, which remember is integrable, times the P pivotality, then we are done. Okay. So now our new goal is just the following. We have a model mu T at parameter P. So T and P are not changing, they are fixed now. You have a vertex X, you have an event A, and you want to compare pivotality, two notions of pivotality. Okay. And you want to prove that changes in T, essentially what this is saying is that a change in T around X is much less effective than changing P around X. This is roughly what this is saying. Okay, so this is our new goal.
So
something like this. Yeah.
And about asking if A it's a local event.
That's a very good question. A is not a local event. So the interest of the whole strategy, the interest of the whole strategy here is really to prove this inequality, to end up with this inequality for arbitrary events A, or maybe not arbitrary events, but for interesting events at any scale, because sharpness depends on it's something about sufficiently large scale. So you don't want it to depend on T, for example. You don't want A, the size of A, to depend on T. You want it to be really arbitrary. Okay. So thank you for the question. You should think of A as a global event. Maybe you take it to local so that the things are differentiable, but the bounds should not depend on the size.
Marcelo Hilario asks you if you need some sort of finite energy property.
For everything I'm saying here, you need a lot of things to make it precise. So it's everything here is so vague that you need a lot of things to make anything like this precise. In particular, finite energy would, certainly. But again, I would just like to give a global view of the thing. And then when it comes to technicalities, like how do you actually prove these things? Well, this can get very complicated, and I was a little bit coward for choosing not to go into that. But yeah, for every specific model you come up with, you will have a different strategy using different kinds of properties of the model. Yeah. But the kind of strategy, the global strategy would be kind of the same, which will always reduce to something like this. Okay, so I hope it's clear. You now what you essentially reduced your whole problem to comparison between two notions of pivotality, whatever that means. for a fixed model around a specific point X. And then comes the key observation that typically, so again, this is too abstract to make precise, but for in practical cases, it will often be the case that that the mu t will be a good approximation of a good local approximation of mu infinity, of the original mu. Okay, but only local. So it's going to be locally a very good approximation, but only locally. And in which sense is this? Is that it is true? In the sense that the discrepancy between mu t and mu infinity is much less important than the discrepancy between mu t and mu t plus epsilon at p plus epsilon. Sorry. So changing p will typically be much more effective than just changing t locally. Again, just this is only locally around each vertex x, but not necessarily globally. Okay, so this will be typically the case. You're going to see, if I have time, an example of that. But then, if that's true, then since t pivotality and p pivotality are notions that are they differ from each other only around x in some sense. Okay. Then what this is saying is that you can compare probably, or with you have some hope of being able to compare the t pivotality with p pivotality by paying a price which is just local, which just amounts to essentially the discrepancy between t and t plus epsilon around x, and the discrepancy between p and p plus epsilon around x. Okay, for every given x. So again, this is it's much more complicated than it's than it looks like here. I'm simplifying things on purpose, oversimplifying things on purpose, but roughly speaking, this is the idea. So roughly speaking, the interpolation, this whole interpolation idea allows us to compare models in a global scale, because A here is a model at any scale. It's a kind of a global thing. We can derive this kind of global approximations from a local one. If around each x things are comparable in this sense that changing t is less effective than changing p, then you can bootstrap that to a global comparison by following this kind of strategy. Because when you look at the derivatives, everything comes down to something happening around some vertex, and then you can compare them. Okay, so this is just again, it's very vague, but I would like to give emphasis to put emphasis on the ideas rather than the technicalities. Okay, so let me give you just one specific example of a model for which we managed to implement this strategy. Okay, so here's the Gaussian free field level sets. I'll be very quick here because I don't want to get too technical, but this is the model we managed to implement this strategy. So the Gaussian free field is a random height function. It's a Gaussian field on ZD, d larger than 3, because we will need the random walk to be transient on it for it to be defined. And it's the centered Gaussian field with covariance given by the Green's function for the simple random walk. So it's just the sum of the probability of hitting y at time n, given that you start at x. So the amount of time you spend at y starting at x for the simple random walk. Okay, so this is a covariance matrix. You can prove that, and then this defines a Gaussian field. Okay, and as you can see, that since this is the case as distance to the power minus z plus 2, this is a very slow decay. So this random function, this random height function, is a quite strongly correlated thing. Okay, so out of this strongly correlated height function, you can construct a percolation model, which is the level set percolation. So for fixed h, a real parameter, this is going to be our play the role of our p in previous slides. We consider the subgraph associated to the vertices that are above h for this random function. So this defines a random subgraph. So this is a side percolation instead of an edge of a bound percolation. So you consider vertices as being open or closed instead of edges, but you can understand it's still a percolation model. You can study the connectivity properties of this random subgraph as h varies, and the theorem we managed to prove is that indeed this model undergoes a sharp phase transition in h. Okay, so that's the result. What I exactly mean by sharp phase transition is something analogous to what you've seen for Bernoulli. Not exactly the same, but something analogous to that. Okay, and then just to finish, I would like just to tell you quickly how we constructed interpolation for this model, which is very simple actually. Then proving the differential inequality is much more complicated. It's very technical, but the interpolation is very easy to define. And I will try to do that in the next 5 minutes if I still have time. I guess I do. So I hope that the model is clear. Now we construct the decomposition, and it goes as follows. So sorry, the interpolation, and it goes as follows. We're going to use the decomposition of the Gaussian free field, and this decomposition is construct as follows. So we consider pk the heat kernel for the lazy random walk. Okay. So instead of considering the random walk, we consider the lazy one. So it's just adding the half in the diagonal for the rate of jumps. Okay, so you can stay put with probability half instead of just jumping to the neighbors. And this has the advantage of being positive definite matrix. Okay, so that's the only reason why we change it to be the lazy instead of the standard random walk. And then you can write the Green's function as a half times the sum of this heat kernels. Okay, the half is just because it's lazy. And then you can decompose this sum, this infinite sum, into finite sums, and that's what I'm doing here. So the G0 is just the first guy, and the GK for every k will be just a partial sum from 2 to the k minus 1 to 2 to the k of this heat kernel. Okay, so like this, you decompose your Gaussian free field because you decompose your Green's function. So G is equal to the sum of GK, right? And if G is equal to the sum of GK and each GK is a covariance matrix, then you can define Gaussian fields psi k, which will have covariance given by GK. And then you can write your phi as being the sum of psi k, just because the covariance matrix of this guy is just the sum of the covariance matrix of this guy. So you have this independent decomposition of the Gaussian free field into infinitely many fields. Okay, I hope it's clear how this is constructed. And the interesting property of this decomposition, so why are we writing phi as a sum, as an infinite sum like that? Well, the nice thing about it is that each psi k for fixed k is a finite range. It has range 2 to the k. That's because the random walk after time up to 2 to the k can only go to distance 2 to the k. It cannot go further than that. So this covariance matrix here is actually 0 for x and y at distance larger than 2 to the k, and therefore the associated Gaussian field will have independence between sites at distance larger than this range LK here. So this is a finite range for HK. This is a finite range Gaussian field. And for large k, this psi k is quite tiny. It's quite concentrated around 0 because its variance is given by the sum of the heat kernel, this kind of tail of the heat kernel. And if you plug the decay of the heat kernel at the diagonal, which is j to the power minus d over 2, then you get this decay here for the variance of each psi k. So you see this decomposes the field as a sum of finite range models, but the guys with large range, the psi k's for large k, they are actually quite concentrated around 0. Okay, so this gives you a way of approximating phi by a finite range field. And that's exactly what we do. So we just define phi n to be the partial sum from 0 to n. And for continuum t between n and n plus 1, we can just take the linear interpolation between the two. Okay, so phi t is equal to phi n plus t minus n times psi n plus 1. Okay, so this defines naturally an interpolation between finite range models, because each phi t is finite range, right? And the original model phi sorry, this is a typo. This t should be just nothing. It should be just the original phi. Okay, sorry for that. So it defines an interpolation between so interpolation for this original model phi larger than h. Okay, I hope it's clear, the construction of this interpolation. And why is this interpolation good? So the important property that we needed in all the heuristic of this strategy I mentioned, I described before, the important property would be that phi t is a good approximation of phi. So mu t is a good approximation of mu. And this is true because the variance of these psi k's are decaying very fast. So you can quickly convince yourself that the probability of phi minus phi t being larger than a certain epsilon would decay extremely fast with t. Okay, so this is telling you that mu t, at least locally, at least around x, each x, is indeed a very good approximation of the original mu. At least if you change the parameter h by some epsilon. Okay, and this is exactly what we kind of need, at least at the heuristic level, to run the argument, and that's exactly what we do. We run the argument. It's actually proving the differential inequality is quite complicated, but essentially the key property is this one, that it's locally a very good approximation, and then we run the argument, the strategy. And then we can import sharpness from the finite range models phi t to the original model.
Marcelo is asking ln is 2 to the power n, Marcelo.
Yes, ln is 2 to the power n, which is just the range of the model. Okay. So yeah. Okay, so I was very vague, I know, but I hope I managed to give an idea of this strategy, which is essentially, roughly speaking, a way again of deriving global comparisons from local ones. Okay, so now I would like just to finish by mentioning a few future directions. So first of all, a natural question is just prove sharpness for other models. Try to implement this strategy for other models. And then, for example, random interlacements, which is a vacant set of random interlacement, to be more specific, which is a model which is deeply related to Gaussian free fields. So this is a natural question. This is actually an ongoing work with the same group of collaborators and Augusto Teixeira. One can look at smooth Gaussian fields. So instead of looking at ZD, look at RD and look at a smooth field and try to prove the same thing. One can also try to prove supercritical sharpness for all those classical models I mentioned, for which, as I mentioned, they are already known to have subcritical sharpness, but not necessarily supercritical sharpness. So this strategy I mentioned works for both at the same time. So one could try to do that. Another more ambitious thing, I don't know if it's science fiction, but a priori the whole idea, the whole strategy may not be very specific to percolation. It may be something more general. So can this idea of deriving global comparisons from local ones be used to deal with long range correlations in other types of probabilistic models? So I know in the audience there are many people, like specialists in particle systems and things like that. So do you see any kind of application of this kind of idea to other contexts than percolation? I think it's not too crazy to think that this could be possible. And last but not least, can interpolation be used to study near critical or critical models? Because all of what I said was about P smaller than PC and larger than PC. So what about P at PC or near PC? So this sounds even more like science fiction, but why not? Okay, so that's all. Thank you very much.
Thank you. So I will please unmute yourself to thank our speaker. So I invite you to unmute yourself. And so I will now open for questions. So, and as you type your questions, well, I have an elementary question. So these are models in which you have a sharpness. So do we have models in which there is no sharpness of in the percolation model in which you don't have this sharpness phenomena?
I guess there are. So probably Marcel is a good person to answer that. So he has worked on a model for which this kind of properties do not really hold exactly, and you have some kind of polynomial decay at in some regimes. So in each kind of for each model you're given, for each natural model you're given, you should think kind of what should be the natural notion of sharpness for that model, right? For example, as an Apollo asked at some point, if you take Boolean percolation and if you take a heavy tail of radius, then there is no exponential decay. So what do you mean by sharpness? So what you mean is just the strongest thing you can imagine, the strongest thing that is okay. So an Apollo actually is the Wilson's. Okay. Anyways, so it's just the strongest thing you can imagine. So for the case of Boolean, it's just that the probability of connecting to distance n is decays at least as fast as the radius of the ball, which not necessarily exponential. So it's a little bit hard to answer your question. I don't know about any very natural percolation model for which this is not. You can always cook up things, and I think the closest to natural model is the one that Marcelo studied. So maybe he can mention that, because I don't have on top of my mind the results about this So Marcelo, could you?
Yeah, sure. I can comment a little bit. So Claudio, what you can imagine is that instead of like for Bernoulli percolation, where you remove bit by bit, like for each edge, let's say you declare it open or closed, you can somehow drill through columns independently. So you decide to remove whole columns of your lattice. And for this model, it seems that deep in the subcritical phase, yes, you have exponential decay. But then as you approach the critical point, then power law decay shows up. This is for some region of the parameters. And throughout the whole supercritical phase, you have some power law decay. So as Franco said, still you need to specify what you mean by sharpness, but at least in this case, you don't have exponential decay. So yeah, so we expect that this should be some signature of non-sharpness somehow. But it's not very unnatural as well. Like if you drill through columns, it's yeah, it's something that you could imagine how to do. And other models with this infinite range dependencies, like Winkler's percolation, they also have this power law decay thing, at least in the supercritical phase. So this has been proved by Peter Gatz in the, I think, 2000 or something like that. And then I don't know about something like ON models, and sometimes you can find some power law decays in some regimes, but.
Thank you. Well, Milton, you have a question?
Yes, always. Okay, so today is not it's not really a question, but it's more like a comment of, about what you said, because it looks of course you call it parameter, no, t, but for me, if you think about it as time, we've been recently working on something kind of similar. So it's a similar strategy. So you want to obtain information for a measure which is complicated. It's a long range, has long range correlations and stuff. So what you can do is that if you happen to find a particle system that has this long range measure as an invariant measure, and you happen to be able to describe, to find the local rules for your particle system, then what we are able to do is that, okay, for small times, the particle system is local, so you understand what is going on. It doesn't change things too much. And what you try to do is to pass through the limit, no? So you prove something for your particle systems at time t. You try to do it uniformly in t, and then you take the limit. And so, in a sense, it's not exactly the same idea, but it's I would say it's fairly close enough. And so talking about that, so I do have a question. So, do you use OSSS in your work, or is not really important?
Oh yeah, so as I mentioned, maybe I didn't mention OSSS, but the result on finite range here. So as I said, it follows in the subcritical phase from this recent result of Domenico Planhoff, and this is the OSSS approach. So you use the OSSS approach to prove subcritical sharpness for finite range.
Okay.
But then you take that as the sharpness for finite range. You take it as a black box, and then you run the whole interpolation. Okay. Does not use any OSSS or anything. It's just the comparison between pivotalities, essentially.
Okay. Yeah, because in our scheme we do use okay, so the equivalent subparticle system of the OSSS is the log-Sobolev inequality. And this is what we use in the particle system level. So it's so there are some parallels that I'm puzzled about how far can you go with this parallelism, because it's as you said, no, it's it looks like a good idea that can be transferred to other.
Yeah, but it's also a little bit unfair. I mean, because I describe the thing in such vague terms that you can.
Yeah, you can fit anything on it. Yeah.
Anything. But yeah, I don't think it's too crazy. I think the key thing is you have some global thing that you want to prove, and you have some local ones, and maybe looking at derivatives is the right thing, because then you somehow manage to localize the changes in parameters around the vertex.
Yeah.
So that's kind of the main idea. Of course, as I said, implementing this is super hard. Even for the example I mentioned, it's quite complicated. But well, why not?
Yeah. Okay. Thank you.
Any other question? Well, if there are no other questions, well, I think we should thank Franco again for this very nice talk. And just remember that we won't meet next week, but the week after, and Alessandra Bianchi will be the speaker. So thank you, Franco, for this very nice talk.
Thank you,
so, bye-bye.
Bye.
Bye, thanks.
Thanks.